What's up, everyone? This is LeetCode 98, validate binary search tree, abbreviated as BST, right? Binary search tree can be abbreviated as this. So we're given the root of a BST, right, of a binary tree, and we basically have to validate if it's valid. So what does valid mean? It means that if it follows the rules of what defines a valid binary search tree, right? So like when we're at a specific node, the left subtree should have nodes that are the values are less than where we're at. And then the right subtree should have nodes with values greater than where we're at, right? So when we're at this 2, everything to the right of this 2 should have nodes that are greater than this 2. Everything at this 2 should have nodes less than this 2. And the same rule applies to the other nodes, right? Like when we're at this 3, if this had other subtrees, right? The right subtree better have nodes greater than this 3. If we branch off to the left, the nodes to the left of this 3 better have nodes less than this 3. Well, technically that wouldn't be the case in this problem because you can't have nodes that are equal to each other. That would not make it valid. And you know that, right? Because of this here, right? This is why it's bolded, right? So what this is telling you here, by the way, in case you can't tell, and pay attention when they bold stuff, right? Because they do that for a reason. It says less than and greater than, but it doesn't say equal anywhere here, right? So for example, if we're at this 2 and we go to the right, and this is also 2, we have to return false. It's not valid, right? If we're at this 2 and we go to the left, it has to be less than, not less than or equal to, but less than, right? So if this 1 was a 2, for example, it would not be valid, okay? And the reason I said it wouldn't be valid when we're at here and we go to the left, we would never have a case like that, because obviously when you go to the left, either we're going to have a 3 and it wouldn't be valid, right, because of this, or we would have a 2, in which case it still wouldn't be valid because this 2 here is equal to this 2 here, right? And everything to the right here should be greater than. Okay, so basically just pay attention to the rules, right? That's what helps you, that's what helps define what you should do in this problem, okay? So we're going to go over an example of how we're going to do this, okay? So we're going to basically keep track of the boundaries of where we should be within when we're traversing this binary search tree, okay? So we start at the root node, okay? That's what we're given. And so we're here at this 2, right? And we don't know what our boundaries are, other than it should be less than, or it should be between negative infinity and infinity, okay? That's basically like our default values where we start, okay? Because again, it doesn't matter what the root node is. It's valid either way. But we need these boundaries here so that we can adjust them as we move somewhere, okay? So for example, when we're at this 2, now let's say we're going to traverse to the left right here, like if we're doing a DFS, right? We're going to start at this 2 and traverse to the left, okay? In which case, this node would change, right? Because now we're looking at node 1, okay? But we need to adjust the boundaries. But what boundaries would we adjust, the left or the right? I mean, think about it, right? When we're at this 1 here, right? We need to be between what? We need to be between negative infinity, right? And this 2 here. That makes sense, right? That's what a valid binary search tree is. Because we wouldn't ever want this node here to be greater than 2, right? Or I should say greater than or equal to 2, right? So the right node would change 2. I call it right. You can call it max also, like maximum or minimum, right? In fact, in the code, I'll just write it like that. But here we're just going to call it left and right. So the way now when we're at this 1, right, we're going to, and we updated these variables here, the boundaries, we're going to say, is this 1 here, if it is less than or equal to the left, or, right, or this 1 here is greater than or equal to 2, if either of those are true, we're going to return false, okay? And that should make sense, okay? Because we never want this 1 to be less than or equal to the minimum or greater than or equal to the maximum, okay? And then obviously we're going to check the 3. We never return false here, obviously, because just by looking at the picture, you can see it's a valid binary search tree, right? This 1 is less than this 2. This 3 is greater than this 2, right? So the answer here is true, right? And this is just example 1, by the way. Now here, right, we're at this 5, for example, right? We're going to have negative infinity here. We're going to have infinity here, right? We're going to go left, and we're going to adjust this would be 1, right? The right boundary would be 5, right? And of course, nothing problematic here, right? This 1 is between negative infinity and 5, right? So we're going to go back up, right? So we're here again, and now we're going to go to the right, okay? Now here's where we are going to run into issues, right? Because when we go right here, okay, this node is going to change. We're at the 4 now. We need to update these variables here, these variables, okay? And so when we're at this 4 here, okay, what is going to change, the left or the right? Think about it, right? Well, we know for sure this 4 better be between infinity and what? And this 5 here, right? And not inclusive, right? So it can't be equal to the 5. So the left would change, right? So we're going to change this to a 5. So we're going to say, okay, is 4 less than or equal to 5? Is 4 greater than or equal to infinity? Okay? And again, these are ors, right? If either of those are true, we return false. So right here, is 4 greater than or equal to infinity? No, that's false, right? Is 4 less than or equal to 5? Oh, actually, yes. So this would be true. We have an or statement here, right? So we actually, if either of those are true, our result should be return false, right? Like programmatically, that's how we would do it. If one of those are true, we're going to return false, okay? Now, technically, I know in like a logical or statement, technically you would return true. That's not what we're doing. The way I'm speaking about this is programmatically. If one of these is true, let's return false. That's basically what we're doing. And the reason I'm stating it like this is because this is how we're going to do it in code. This is how we're going to check whether we have a problem or not, okay? So if either of those are true, right, it means we have an error in, like, think of it like that, right? If either of these are true, it means we have an error in our binary search tree, in which case we just want to return false, right? Which makes sense, right? It's not a BST, right? When we're here, everything to the left should be less than this 5. When we're here, everything here should be greater than this 5. Well, look, this 4 is not greater than this 5. This 3 is not greater than this 5, right? So we have issues. So our final answer is we're going to have to return false. This is not a valid binary search tree, right? This is example 2, by the way, okay? And there's an explanation here if you want to look at it. Right, we don't have any weird edge cases where we can have like 0 nodes or something, so we don't have to like write an edge case for that, so that's good. But let's program this out, okay? So, first of all, we're gonna create a function, but before we do that, we'll just call this, we're gonna create a function called validate, okay? And again, starting off, what are we gonna, remember when I was going through those examples, starting off, what do we have? We have a node, right? Our root node, right? Our root node, and we have negative infinity as the left boundary or the minimum, and the right boundary or the maximum, right? Whatever you want to call it, is infinity, okay? Negative infinity and infinity, those are our boundaries in it. Now let's create this function, okay? So we're going to say define validate, and we have a node, and then we have a minimum and a maximum, okay? So, this is just an edge case, right? So if we're at like a node and we go left or right, and there aren't any child nodes, like when we're at this 1 here and we go left or right, obviously there's no child nodes. So just return true, okay? Because that's not a problem. If we don't have any child nodes, that's fine. Okay, now here's where we would check, right? If remember our statements on where we would return false, right? If the node that we're at, right, is less than or equal to the minimum, right? The minimum, we're going to return false. Now we have another case, which is if the node that we're at is greater than or equal to the maximum, right? That makes sense, right? When we're here at this 5, for example, and we go to this 1, right? This 1 better be between negative infinity and 5. But again, remember what I said up here. It has to be less than or greater than the node keys. So if this 1 is equal to the 5, that is not a valid BST, which is why we have to say greater than or equal to. If it's greater than 5, it's problematic. If it's equal to 5, it's also problematic, right? So I mean, you can also write this basically by saying not to return false, but to validate whether it's okay. Think of it like the condition of this node here has to be less than 5, right? Now if it's greater than or equal to 5, right, the opposite, that's where we have a problem, right? Because this right here is just saying, okay, this node has to be less than 5. If it's not less than 5, we have to return false. Okay. Just this condition here, right? Make sure you understand it. It's really the bulk of how we're checking our boundaries, okay? I don't think it should be too difficult. But people write it different ways, I think, depending on what solution. Like some people might structure this function a little bit differently, but do whatever's most comfortable for you in terms of how you logically can think about it. But this is just how I wrote it. Okay, now here's where we're going to recursively traverse the tree, right? So we're going to say, now when we go to the left, right, the node that we're passing is obviously node.left. And again, when we go to the left, what are we doing, right? The minimum is staying the same, but the maximum is getting updated. So when we're at this 5 and we go left, the minimum is staying the minimum, right? That's what our inputs are, but the maximum would change. What would our maximum be? It would be the node we were at, right? So we're actually just going to say node.val, okay? Additionally, we need to continue to traverse this tree, so we're going to have to handle the right nodes also. So we're going to say node.right. And again, when we go to the right, what are the boundaries changing? The maximum should be the same, but the minimum will get updated to where we came from, right? So here we would say node.val, and here we would say maximum, okay? Now, this is an AND statement, so if at any point in our BST as we're traversing it, if at any point it's false, this is going to return false, and which is what we want, right? Because if at any point our BST is problematic and it doesn't follow the rules, we want to return false for the entire thing, okay? Up here, then we can run this. If node, oh, I said node, I don't know why. If node is node. I meant to say if node is none. Okay. Yep. So that's passing our test cases, nice. Right? This is a very short and sweet solution, right? Don't overcomplicate it. Yeah. We submit. But yeah. Like I said, I could have made this video a little bit shorter, but I just wanted to go through the examples, make sure you understand what we're doing in our code. So hopefully you found this useful, and I'll see you in the next one. Peace out.